Making it through General Chemistry 1 is an achievement worth celebrating. You've built a foundation in the basics of chemistry: atoms, stoichiometry, gases, and bonding. When students walk into General Chemistry 2, the very first major topic is often intermolecular forces, the attractions between molecules that explain boiling points, solubility, viscosity, and many other physical properties. But before you can truly understand intermolecular forces, you need to be comfortable with some key skills from General Chemistry 1. To identify intermolecular forces properly, we need to be able to draw Lewis structures, know the correct VSEPR shape, and then identify if the compound is polar or nonpolar. These skills will set us up to do well when we have to identify the intermolecular forces for the compounds. The very first skill to review is drawing Lewis structures, because you can't talk about polarity or intermolecular forces unless you can first see how a molecule is put together. Lewis structures show which atoms are bonded, how many bonds are present, and where the lone pairs are. The placement of lone pairs influences molecular shape. The shape determines whether the molecule is polar or nonpolar. For Lewis structures, we can use these rules to help us draw the molecules quickly. The best Lewis structures minimize the amount of formal charge on each element. The goal, if possible, is to have each element equal a formal charge of 0. If we do have charges, the negative charge should be on the most electronegative element, and the positive charge should be on the least electronegative element. We have some simple steps to draw the Lewis structures. Number 1, try to make the structure as symmetrical as possible and connect each element to the central atom once. Number 2, look at these bond trends and make sure each element has the correct number of bonds to have a formal charge of 0. Boron's group likes to have 3 bonds, carbon's group likes to have 4 bonds, nitrogen's group likes to have 3 bonds, oxygen's group likes to have 2 bonds, and the halogens like to have 1 bond. And hydrogen will have 1 bond. In the last step, add in electrons to make each element have a formal charge of 0. To calculate formal charge, we will look at the number of valence electrons for that element from the periodic table and subtract that from the number of connections that it has in the structure. To count connections, 1 bond is equal to 1 connection, and 1 electron dot will also be equal to 1 connection. For example, if I was drawing CO2, the first step is to try and make the structure as symmetrical as possible. There's only 1 carbon, and carbon is the backbone for molecules, so it will go in the center. If you are ever unsure about what molecule goes in the center, the least electronegative element, excluding hydrogen, will go in the middle. Next, I'll connect each oxygen to carbon, 1 on either side to make it symmetrical. Using the second step, I will make sure each element has its correct number of bonds. Carbon's group likes to have 4 bonds, and oxygen's group likes to have 2 bonds, so I will double bond each oxygen to carbon, so each element is happy with its correct number of bonds. We can have single, double, or triple bonds between 2 elements. Next, I'll make sure that each element has a formal charge of 0 by looking at the number of valence electrons the element has from the periodic table and comparing that number to the number of connections that it has in the Lewis structure. To have a formal charge of 0, the number of valence electrons must equal the number of connections in the structure. To count connections, look at what is surrounding the element of interest. 1 bond is 1 connection, and 1 electron dot is also 1 connection. Oxygen has 6 valence electrons, so each oxygen in my Lewis structure needs 6 connections to have a formal charge of 0. Right now, the oxygen on the right has a double bond. Each bond counts as 1 connection, so it has 2 connections. I will add in electrons to make sure that the oxygen has 6 connections total. I need 4 dots to make this oxygen have 6 connections. The dots have to be arranged in pairs, so I will have 2 lone pairs on oxygen to make 4 dots total. If an electron dot is alone, this is a radical, and radicals are not very stable. I will do the same thing for the other oxygen. It has 2 connections right now, so I will add 2 lone pairs to make 6 connections total. Carbon has 4 valence electrons, and it has 4 connections, so it has a formal charge of 0, and no electrons need to be drawn. If you're comfortable drawing Lewis structures for molecules like H2O, NH3, CH4, CO2, and SO2, you're ready to move on. Once you have the Lewis structure, the next step is figuring out the 3D shape using valence shell electron pair repulsion or VSEPR theory. This is important because the geometry determines whether polar bonds will cancel each other out or add up to create a larger overall dipole moment, which is the key to predicting polarity. The main thing that's going on here will be electron pairs or lone pairs repel each other and arrange themselves as far apart as possible. To be able to look at the shapes, also known as molecular geometry, we have to be able to count the number of domains around the central atom. Domains can be bonding and non-bonding domains. Bonding domains are single, double, and triple bonds, and non-bonding domains are lone pairs. The common shapes to review will be linear, with 2 domains and 180-degree bond angles. An example will be CO2. Trigonal planar with 3 domains and 120-degree bond angles. An example will be BF3. Trigonal planar bent with 3 domains, but one of those domains is a lone pair. Trigonal planar bent will still have a bond angle of approximately 120 degrees, but slightly smaller due to the lone pair creating greater repulsion. An example will be O3, also known as ozone. Tetrahedral with 4 domains and 109.5 degree bond angles. An example will be CH4. Trigonal pyramidal with 4 domains, but one of those domains is a lone pair. Trigonal pyramidal will still have a bond angle of approximately 109.5 degrees, but for an exact angle, it will be slightly smaller with a bond angle of 107 degrees. An example will be NH3. Tetrahedral bent with 4 domains, but 2 of those domains are lone pairs. Tetrahedral bent will still have a bond angle of approximately 109.5 degrees, but for an exact angle, it will be slightly smaller with a bond angle of 104.5 degrees. An example will be H2O. Trigonal bipyramidal linear with 5 domains, but 3 of those domains are lone pairs. Trigonal bipyramidal linear will have bond angles of 120 degrees around the lone pairs in the center, and the bonding domains will be at an angle of 180 degrees away from each other. An example will be XeF2. Octahedral square planar with 6 domains, but 2 of those domains are lone pairs. Octahedral square planar will have a 90-degree bond angle in the center where all of the bonding domains will be, and the lone pairs at 180-degree bond angles away from each other. An example will be XeF4. Now that you know the structure, the next question is the molecule polar or nonpolar? Here is a fast way to determine if the molecule is polar or nonpolar. You only need a Lewis structure and the VSEPR shape. A polar compound will be unsymmetrical, and this means that there is an unequal distribution of electrons. A compound is polar if there are lone pairs on the central atom or different elements surrounding the central atom. An exception to this rule is if the VSEPR shape is trigonal bipyramidal linear or square planar octahedral, it is a nonpolar compound overall when there are the same elements surrounding the central atom. A nonpolar compound will be symmetrical, and this means that there is an equal distribution of electrons. A compound is nonpolar if there are no lone pairs on the central atom and the same elements surrounding the central atom, and you have to have both. Let's practice a few. Carbon dioxide. Carbon has no lone pairs and has the same element oxygen surrounding the central atom, carbon, so the molecule is nonpolar. Water. Water has lone pairs on the central atom, so the molecule is polar. Boron trifluoride. BF3 has no lone pairs on the central atom and has the same element F surrounding the central atom, so the molecule is nonpolar. Ammonia. NH3 has a lone pair on the central atom, so the molecule is polar. Dichloromethane, CH₃Cl2. CH₃Cl2 has 2 different elements, Cl and H, surrounding the central atom, so the molecule is polar. Xenon difluoride, XeF2, is trigonal bipyramidal linear, so even though there are lone pairs on the central atom, this is one of our exceptions because they cancel each other out in the center. This molecule is nonpolar. Xenon tetrafluoride, XeF4, is octahedral square planar, so even though there are lone pairs on the central atom, this is one of our exceptions because they cancel each other out top and bottom. This molecule is nonpolar. Use the checklist every time. The same atoms around the center and no lone pairs gives a nonpolar compound. If either of those 2 conditions are not met, call it polar unless you are in one of the 2 exception shapes we highlighted, square planar octahedral or trigonal bipyramidal linear. With a little practice, you will be able to glance at a Lewis structure and call out the polarity with confidence.